Yes.
Okay.
So our next speaker is Vincenzo Donofrio from Michigan State University. It's also starting his senior year in the next few days. And this summer, he was working with Jürgen Roth, David Meyer, and Brian Svoboda. And I'll leave it to you now, Vincenzo.
Yep, thank you, Anna. All right. Today I'll be discussing star formation in Sagittarius B2, the galactic center's complex giant molecular cloud. And so in the center of the Milky Way galaxy, we have this region known as the central molecular zone, or the CMZ, which is about 500 parsecs wide. And due to the large amounts of dense molecular gas in this region, it has a pretty high star formation rate of around 0.1 upwards of 0.8 solar masses per year. And when we place this in the scale of the entire Milky Way galaxy, which is roughly 30 kiloparsecs, it only has a rate around 2 solar masses per year. And so the CMZ corresponds to a pretty significant portion of the entire star forming activity in the galaxy. And so if we look at this image here, we can see around the inner 200 parsecs or so of the CMZ. At the center, we see the supermassive black hole, Sagittarius A star, and all the molecular clouds in this region orbiting around the supermassive black hole. While the black hole is not a region of much star forming activity, as we increase our distance from it, the activity slowly increases. So for Cloud Brick has some star forming activity, Cloud ENF has a little bit more, and then Sagittarius B2 has even more. What's interesting about Sagittarius B2 is that its star forming activity is even higher than what we might expect for the gradual inclination here. And so my project will be focusing on the very complex nature on Sagittarius B2 and characterizing the gas and how it illustrates the star forming features in the cloud. So Sagittarius B2 is the largest molecular cloud near the center of the Milky Way galaxy with a width around 40 parsecs. And also a total mass around 10 million solar masses. Looking at this image to the right here, which is a composite of X-ray and radio data, we can see around the inner 20 parsecs or so of Sagittarius B2, which coincidentally corresponds to 99% of the mass of the cloud. And so the red shows the radio data and the white shows the bright radio continuum peaks. And in Sagittarius B2, there's two hot, dense cores in the center of its region that is well known for very high star forming activity. And so the overall goal of the project is to characterize a gas that illustrates star formation in Sagittarius B2, particularly including north and main, but particularly analyzing the different regions around the cloud. So the data we'll be using to achieve this is the survey of water and ammonia in the galactic center, or SWAG. This data was collected using the Australia Telescope Compact Array, which is an array of 6 22-meter antennas, and it observes a total of 42 spectral features plus radio continuum over the range of around 21.2 gigahertz to 25.6 gigahertz. And so the neat thing that SWAG offers is its overall goal is to map the molecular content of the central molecular zone. And so in relation to my project, we'll be able to consider multiple regions around Sagittarius B2 simultaneously, whereas most studies particularly zone in on the north and main regions. And so the regions I picked for Sagittarius B2 correspond to that inner 20 parsec region, and also looking at this image corresponds to the white peaks, which are the white spots, which are the bright radio continuum sources. And so the 10 sources here in this image here, not including the two southernmost sources, correspond to sources that are heavily ID'd in the literature. And but these two southern sources don't appear in the literature, and so we kind of give them placeholder names of Southern Extra and Southern Extra 2. And again, this image is not a part of the SWAG data set. It's a composite of X-ray data from Chandra telescope and radio data from the Meerkat radio telescope. And I'm using it instead of the swag because it offers more of a visual appeal, it offers more of a visual appeal than the swag dataset. And so before we go on to characterizing the gas in Sagittarius B2, I should highlight some relevant steps in the data preparation. And so the swag dataset, as I said, offers 42 spectral features, but a few of these may be contaminated or duplicate lines there. And so we need to identify which lines are in fact the line that they say it is, and remove those that aren't. And so that's left me with 28 spectral lines remaining. And so how I want to characterize the gas is I want to compare each line to a reference source so we can kind of understand how each of the molecules compare against each other in the data set. And so the reference line I'm choosing is ammonia 3,3. As in the SWAG data set, it's the most established column density tracer. And so it should serve as a good reference. And so what exactly we want to compare is what we want to compare are the emission and absorption components that correspond to velocity components in the Sagittarius B2 range, which is 0 to 100 kilometers per second. And so this image shows an example of reference for ammonia 3,3 in the L region. And so what we want to do is Gaussian fit this bright emission peak here, and it corresponds to around the velocity of 70 kilometers per second, which is well in the range of Sagittarius B2. And then for each other line that we're comparing to it, we want to find the corresponding emission or absorption component at that corresponding velocity. And the fortunate thing is that 11 out of the 12 regions for ammonia 3,3 served as very good references, except the U region. And so what we did for there, we substituted ammonia 1,1 as a meaningful reference for the U region. And so to compare the molecular gas of Sagittarius B2 and to understand how it illustrates the star-forming features in the cloud, we want to zoom in on the specific set of molecules that we have remaining that relates to the star formation. These specifically include the non-metastable ammonia, complex organic molecules, and shock tracers. And so to understand what's going on here in each panel, we can zoom in on this top right corner in ammonia 6,6. And so what we're seeing here are the red peaks correspond to emission components that correspond to the velocity component of the reference. And the blue bars here correspond to the absorption components at that reference. Some panels include blank spots in some regions, and these are simply due to the fact that there was no discernible emission or absorption component at that specific Sagittarius B2 velocity. In other words, they're simply we couldn't separate those components from the noise, and so they're not significant data points. And so my first result checks the expected temperature distribution in Sagittarius B2, and we can use a couple of metal metastable transitions of ammonia as a sort of as a molecular cloud thermometer for the B2 cloud. And so by using, in this case, ammonia 2,2 and ammonia 4,4, these line ratios incorporate the ratio of the brightness components. So as long as we have that, and we have their complex, we have their quantum numbers, and we also have the energy difference between those two transitions, which is a constant, we can find the rotational temperature. And so for the emission components, we can use the ratio of peak of brightness over brightness. But then for the absorption, we need to convert to the optical depth tau using the continuum, the continuum temperature value, which is given in the SWAG continuum map, and then we can correctly find the temperatures that correspond to absorption. And so looking at this image on the right, we see a color bar that corresponds to the rotational temperature of the various regions throughout Sagittarius B2. We expect what we see here, we expect the inner regions of the cloud to be hotter, and as we gradually go out to the outskirts to cool off. And we observe this trend generally, but two components that stand out is region M and region U. Region M is a lot cooler than we expect in this image, and that simply can be done, as we can see here, for at least for 2.2 and 4.4, M is in absorption, and so we should expect a cooler temperature for our data, but why it may be cooler than what we expect than what some of the literature says about a hotter temperature is because we could be not observing proper M, but we could be observing the line of sight of M, and so we could get an influx of some of the outskirts, the cooler outskirts of the cloud, and that could be damping that temperature. And then to note U, and for the 2.2 and 4.4 transitions, one is in emission and one is in absorption. So we can't find the rotational temperature for that, as they have to be either in both, or they have to be in either both in emission or absorption. And so we also can't, we can also use maybe another pair of transitions, but it's a little more complicated than that. And we kind of have to do a more complicated thing and kind of construct all the components of the transitions. And so finding a temperature view is not so straightforward, so we have to leave it blank for now. And so to understand how the gas of specific star-forming molecules, star-forming molecules can kind of illustrate the star-forming picture of the cloud, we can now zoom in on different types of star formation tracers. First is non-metastable ammonia. And it's good to trace star formation because in the presence of background infrared radiation, its rapid decay into the metastable ammonia states allow for a discernible tracing of the radiation environment within star formation regions. And so looking at this graph here, looking at these plots here, we can see that North and Main are extremely dominant, but U is also consistently present. Another thing we can note here is that the main region M is bright in emission, which kind of gives credence to what we saw in the last slide, which is that perhaps we are looking at not proper M, but along the line of sights of M as the non-metastable ammonia states predicts a hotter temperature for M. So another set of star formation tracers are shock tracers and complex organic molecules. And these both correspond to, they're both abundant on ice grain surfaces. And so when a star forming triggering event, like a cloud-cloud collision or a supernova or nearby supernovae occur, they shock the shock tracers and complex organics in the cloud and disperse them throughout the cloud into a gas phase, and therefore they can kind of trace the star formation. And again, we see here that North and Main are pretty dominant, and then but U is also a consistently high region, and so we can kind of note that again. Another thing to note is that North and Main are likely not due to shock, but simply because of their very high temperature. The abundance of these molecules could be possibly just due to evaporation, whereas the rest of the regions are predictably not hot enough to have this abundance in evaporation, so they're more likely to be shocked. And so what we've done is we've characterized the gas in Sagittarius B2 to kind of illustrate star forming features. And we've shown that North, Main, and U are similar in that regard. And so to kind of wrap this all together, we want to kind of understand why this kind of triangle here, looking at this middle image, kind of possibly exhibits more star forming features than the rest of the cloud. And the Hasegawa model from a 1994 paper states that the overall star forming activity in the cloud is possibly due, or actually likely due, to a cloud-cloud collision in this kind of northwest edge. So looking at this image on the right, we can kind of understand what the model states here. And so the model states that this dense clump that we see here collided with a less dense cloud and ripped kind of a hole in the cloud and removes some of the gas with it. And we can also note the north main and south regions. And so look, kind of comparing these maps, we would see that we have north and main here, and that U could possibly be on this most western edge here. And so because of the cloud-cloud collision that occurred given from this model that ignites the star formation in the entire cloud, it would make sense that since U is very much a part of this collision, that U would be, along with north and main, a highly active star forming region. And so that kind of leads me to the further work that I would like to do on this project, which is to kind of explore kind of more sources and see if they can be consistent with this model, with this Hasegawa model. So I would specifically look into sources that are not bright in the radio continuum, and specifically in this kind of northwestern region here, to possibly see if there's any correlation with the possible cloud-cloud collision. And since another thing to kind of note here is that region U is extremely understudied in the literature, and so there's really only maybe basic descriptions of the region given. And so another thing that would be interesting would be to try to constrain the star forming rates in that region to see if we actually kind of quantitatively observe higher star formation in the cloud that would maybe kind of bring this possible cloud-cloud collision model together a little bit more. And so I would like to acknowledge the mentors that helped me along the way over the summer with this project. I would like to give thanks to Dr. Jürgen Ott, Dr. David Meyer, and Dr. Brian Swoboda, and the entire NRAO. Thank you.
Thank you, Vincenzo. That was great. Questions? Please feel free to either raise a hand or just unmute yourself. I have to admit that I had a question, but your previous slide just answered all of it. So well done.
Good.
Yeah, it was pretty good explanation. I like that.